so, but maybe say it in a slightly different way. Okay, so here is the deal. We have this thing called the Fundamental Theorem of Calculus, which is the focus of the second semester. Okay, that's the big deal. So what it looks like is this. We said that this big, long, elongated S is called the integral symbol. Okay, you wrote that down, right? It's the integral symbol. And A and B are called A is called the lower limit of the integral, and the B is the upper limit. So we have the lower limit and the upper limit for the integral. And the way this works is you put the function, which is the derivative, here, and x is the variable that you're integrating with respect to. Okay, so it's f prime of x dx. And the result of this is equal to f of b minus f of a. And that's the fundamental theorem of calculus. Okay. Now, what it's really saying is you can use the derivative to find out the actual amount of change in the function. You can tell a lot about a derivative, about a function from its derivative. Okay? And so not only can you tell where the function is increasing or decreasing by using the derivative, you can tell how much it's increasing or decreasing by performing an integration. Okay? Now, to show you how this would work with just different letters, because sometimes it's just like weird, you could have a function that looked like this. I go from 3 to 5 of w prime of t dt would give you w of 5 minus w of 3. Look carefully at that notation and compare the two. This says I'm going to work with this derivative of w, okay? And by looking at the derivative of w on the interval from 3 to 5, I can tell you how much the function is changing, the w function is changing on that interval from 5 to 3. Okay? Does that make sense? All right. The other thing that we said was if you had a function, and I guess as long as I got that one, I got from 3 to 5 here, and it's some derivative, and it can do anything it wants to. Okay. So let's pretend that this is w prime of t. Okay, that's what this one is. Okay. And the interval from 3 to 5, what this means is if I draw a vertical line here at 3, and I draw a vertical line at 5, the area that is bounded by the derivative and the t-axis, in this case, rather than the x-axis, this area right here tells you how much w is increasing by. The area right here, which is bounded by w prime and the t-axis, tells you how much that the function w is decreasing by. If I look at the entire interval from 3 to 5, I'm actually looking at the net change in the w function from 3 to 5. Now stop and think about this. By just looking at these two areas, which section of the area looks bigger? The bottom one does. This looks bigger than this. Okay? So if I were to try to figure out what the function looked like, and suppose this is at 3. This value right here is w of 3. Okay. And over here, this is 5. Would w of 5 be above or below where w of 3 is? Would be below. Okay? Because look at what happens here. Doesn't this tell you that the function w is going to increase? So it's going to increase whatever this amount is. So let's just pretend that that amount, and this is the part where it stops, and this is where there's a maximum. Let's pretend it goes up to right here. This change from here to here is equal to the area right here. But then this area is equal to the amount of change that the function is decreasing. And we all agreed that this was a bigger area than that one. Therefore, the answer for where w of 5 would have to be below where w of 3 is. Like that. W of 5. See what I'm saying? Now, I just did an estimate here, but if we actually knew what this area was, and we knew what this area is, we'd be able to tell you the net change, and the net change is the distance between wherever this one is and this one. This is the net change as I go from time equals 3 to time equals 5. Make sense? Okay, we're going to do a lot of looking at areas and then derivatives, these integral things, using our calculators, and then trying to figure it out by hand as well. And that's what is expected of us. All right, we have an example that we started yesterday. We did an easy one first, and we're doing a medium one, and we're going to do a hard one. Okay, so take a look at this. Did we have that f prime of x was equal to x plus 4? No. That was in your notes from yesterday. And then Swivl star. And we said we're going to go on the interval from -9 to -5, right? Okay. And so yesterday we drew this. We drew the graph, right? And the graph was the graph of f prime. Okay. So that's the graph of f prime, and this is from -9 to -5. And then we said, oh, look at that. The derivative is below the x-axis. That means the function is decreasing on the interval from -9 to -5. So then we figured out this area. And what did we figure out that area to be? That area was equal to what? 12. Okay, right? Okay. That area is equal to 12, and we notice that the area is below the x-axis. So, did we say this? We said therefore, I don't know if we got to this point. Did we say therefore? Yeah. Therefore, f is decreasing 12 units on the interval from -9 to -5. So we got to that point? And then did that when we finished? Okay, sweet. So we're going to pick up where we left off now. And where's my clicker? All right, so what I want to do now is prove this. Okay, so we made this claim that the function is decreasing 12 units. So now, let's go try to prove it. Okay. So to prove it, we need to know what f of x is. So let's suppose we say here, if f prime of x was equal to x plus 4, then f of x is equal to what? Adjustment needed. F of x is equal to what? This is where you come in.
X squared over 2 plus 4x.
X squared over 2 plus 4x over 2. Okay? Everybody do that math in your head now. You're going backwards now. Okay? So look at this function. Find the derivative of this function in your head. What did you get? 2's cancel, right? So did you get x plus 4? So this is good. Now, this is what we call, now listen to the wording. This is n, as in an, n antiderivative of f prime. It's one of them. How many antiderivatives of f prime are there? An infinite number. And the reason is because we should add on the fact that you can add on any number on the end of this, any constant. C can be any real number. Because if you take the derivative of this f of x, you get x plus 4, because the derivative of the c is equal to 0. Okay? All right, so what we're going to do is we're going to do a little test. So I'm going to have you probably grab your calculator, and you're going to help me out with some functions. So I'm going to do a test with different functions. So my first one is f of x is equal to, if you don't mind, I'm going to write this as 1/2 x squared plus 4x, I don't know, plus 7. That's my lucky number today. So let's pretend f of x is equal to 1/2 x squared plus 4x plus 7. The derivative of this is this. Okay? So how much does this function change from the interval from -9 to -5? Well, if we could figure out what each of these are, then we could do that math. And since we're going from -9 to -5, and we're trying to find that change, we're going to do f of -5 first, and f of -9 second, and we're going to find the difference. Okay, this is where you come in. I need an answer for these. What'd you get?
-5, I got
-0.5?
-0.5.
-0.5?
Yeah.
And -9. $11.5? Anybody else get that? 11.5? Okay, we agree? Okay, now, watch what I'm going to do. Draw a line and put a big subtraction sign here. Okay? This minus this, watch what I'm going to do here, is f of -5 minus f of -9. F of -5 minus f of -9. And what's -0.5 minus 11.5? -12. Okay. Now it produced a -12. That's kind of interesting. Produced a -12. We said the function is decreasing 12 units. Okay. F of -5, the change here shows that it's -12. Okay. Now, I want to prove this using the calculator as well. So what I want you to do is grab your calculator, and we're going to draw this function, and we're going to identify where these points are and what this is going to look like. So Here we go. So go to your y equals, and we're going to type in this actual function, okay? 0.5, so I'm doing 0.5 x squared plus 4x plus 7. That's my function. And first of all, I'm going to do just a zoom 6, see what this thing looks like. I spy a parabola. Okay. And let's focus on what's actually going on here. So I'm going to draw. Whoa, that was deathly. So I got myself a parabola. Looks something like this. Here is negative 9. Here is negative 1, 2, 3, 4, 5. Looks like it goes over here. Negative 5. So since we're only focusing on the interval from negative 9 to negative 5, this is where I'm looking at, from here to here. Negative 9 to negative 5. Okay. So go ahead and hit trace and plug in negative 9. And what this one is here, this is at 11.5. Right here. That's 11.5. And then go find the y-coordinate for negative 5. So hit trace again, and then negative 5. And you can see this one is negative 0.5. Okay. That's where those two match up. So it's clear from here that on the interval from negative 9 to negative 5, the f of x function, okay, the f of x function decreases a total of 12 units. See what I'm saying? Okay. Therefore, the summary statement that includes the fundamental theorem of calculus, we can say this. The integral from negative 9 to negative 5 of the function x plus 4, because remember this is where the derivative goes, and that's what we had, x plus 4, is equal to f of negative 5 minus f of negative 9 which we figured out to be f of negative 5. This was negative 0.5 minus 11.5, and the answer was negative 12. Does it make sense? Okay. Let's go back to, now I'm going to have us go to the y equals, and you can clear that function out, and I want you to put in the derivative. We're going to graph the derivative, y equals x plus 4. So make your y1 function be the x plus 4, and do a zoom 6 to graph it. We've done this dozens of times now. Here's a derivative on the interval now from -9 to -5. Is the function increasing or decreasing? It's decreasing. But now we get to ask the question, how much is it decreasing by? And we can ask the calculator to give us the answer. So let's go have the calculator do that. Press second, calc. And then go down to number 7, which is your little integrator. Okay. And it asks for the lower limit, which is the left number. So lower left, which is -9. And then the upper limit, which is the right one, -5. And it shades it, and it tells you how much it's decreasing by. So the derivative not only tells you where things are increasing or decreasing, it tells you how much it's increasing or decreasing. Does that make sense? Okay. Now, let's go on to one more. So let's do a hard one. So, and again, these are examples of the fundamental theorem of calculus. We aren't actually proving the fundamental theorem. We're demonstrating that it works for these situations. Okay. All right, so this time, my f prime of x is going to be x squared minus x minus 12. And I'm going to have my interval be from 0 to 8. And I want to know, what is the change? What is the change in the function f, not f prime, what is the change in the function 8 f of x on the interval from 0 to 8? Okay. Go get me the answer. I don't care how you get the answer. Get me the answer. Yes. 42.6 repeating. So, answer 42.6 repeating. And what does that number represent? Okay. This number, if it's right, is the amount of change in the f function from x equals 0 to x equals 8. That's what that number is supposed to mean. Okay. What's weird? What's going to be weird about this one? It increases and decreases. Okay. That's why this one's weird. Okay, so it increases and decreases. All right, so how do you propose we do this problem? Jamie, how the heck did you get that answer?
I used my brain from what we learned in class to use the calculator to get the answer, so when I hand write it out, I can check it to make sure I'm on the right track.
Absolutely. Very good. So what'd you do? Let me see it. Let me hear it. What'd you do? Tell me what you wrote. Yeah.
So I went to y1 and I plugged in the derivative, so x squared minus x minus 12.
Okay, everybody do that right now. Grab your calculator. Have you all done it already? Okay, if you haven't already done it, go do that. Okay, then what's the next step?
Then I hit the graph button.
So-
I fix it.
Okay, so tell me what this looks like.
It's parabola.
It's a parabola. What else? What are the zeros of the parabola?
Negative 4 and positive 4. I'm sorry. It's negative 3 and 4.
Okay, negative 3 and 4. Can anybody do a quick mental check to tell me why that's correct? Yeah, this one factors. Okay, x minus 4, x plus 3. Therefore, when is this equal to 0? At 4 at negative 3. Boom. Okay, so the derivative is equal to 0 here and here. Okay, then it's a parabola. Is it facing upward or downward? Up. Okay.
Negative 12 is the y.
Okay, thank you. Okay. So, I don't see the answer yet.
So then I hit second calc,
Okay.
number 7.
Okay.
Integral.
And what happened?
And I plugged in the lower limit, I hit 0.
Okay.
Entered. The upper limit, I hit 8 entered, and it gives me the answer of 42.6.
Okay. So, let me guess. It shaded this region and this region. Everybody get that? Okay. So, and that's where it gave you, it's the combination of these two, okay, that's the key, that gives you this answer. Yes? Since the answer is positive, that means on the integral from 0 to 8 that the net change in the function went up. Okay? Which means that the area that's above is more than the area that's below. Okay? So, the way that we write it is, now this is our summary statement. Okay? We say the integral from 0 to 8 of x squared minus x minus 12 dx is equal to f of 8 minus f of 0. And this is equal to 42.6. Repeating. Yes. It's both. They don't give you any crazy ones. Like, we're going to use our calculator to just, we're going to actually compute this one to see if this actually works. Yeah. But you're going to have to know how to use your calculator to do this. But you're going to also have to know how to do it without the calculator. But you won't do any really super crazy ones. Well, maybe. Yeah, we'll have to do some crazy ones. I forgot. Okay, so now look at this. This, yes?
So for the ones that we do not have a calculator for, will we need to do a graphic view as well?
No. But you'll have to be able to study a graph and say, oh, is my net change positive or negative? Things like that. Okay? And we're going to also have to find what C is on specific problems and so on. Now everybody look closely at this. You see this whole integral statement right here? This statement, what it's saying is, hey, if I give you this derivative right here, and I give you this 0 and this 8, this means it's the interval from 0 to 8. This means that the net change in f, the function, not the derivative, the net change if I go from 0 to 8 is, now look it's equal to f of 8 minus f of 0. Duh. F of 8 minus f of 0 is going to give you the net change on the interval from 0 to 8. Just subtract the 2. And that gives you it. But this is the notation that we use. We use this goofy integral symbol in order to identify the net change, and the net change is 42.6. Okay? Now, just for fun, what I want you to do is calculate. I want to know, what is this area right here? Tell me what this area is equal to. Go figure out how to do it on your calculator. Does it make sense if you go from 0 to 4? Okay. Question or answer? Answer? Everybody get that? Okay, integrate from 0 to 4. This area is equal to, oh, would you imagine that? It's negative. Because that's the amount that the function is decreasing by. So it's a negative. It tells you how much it's decreasing by with it including the negative. Okay? And then what about here? What is this area? $77.3 repeating. And that we went from 4 to 8, correct? Okay. So take 77 and add it to a negative 34. Just add those two numbers up. Because one's positive and one's negative. We're going to add the two up. And did you get 42.6 repeating? Okay. This shows you that, okay, on the interval from 0 to 4, the function rose or went down negative 34.6 repeating. And then once it hit this 4, then it started going back up, and it went up 77.3 repeating. That's what's going on. But I'm asking in the question, how much did it change if I go from 0 to 8? So we have to combine when it's increasing and when it's decreasing. Okay? All right. Let's finish this off by figuring out what the function is and then testing it. So if this is a derivative, I want to know what an antiderivative of this would be. And we have an answer. Try, go ahead. What's the last part? Plus C. Okay, everybody mentally check that out. When you take the derivative of this, do you get that thing over there? Okay. Now, I haven't taught you how to do this yet, so people who are figuring it out, that's cool. Okay, that's awesome because you're thinking about it. But if that didn't appear to you out of nowhere, don't worry about it. But we'll be learning that. So this is called it's called the antiderivative because now it includes the whole family. Okay, let's pick a value and let's do the same thing we did before and let's just see if this actually works out. So, all right, somebody gets to give me a function. 1? Or a C value? Okay, the C value is positive 1. Okay? I was thinking 17/3, but, you know, to each his own. Okay, so I need f of 8, and I need f of 0. I'll do the hard one. 43.6. So if you were to graph this cubic function, and then you just focus on the interval from x equals 0 to x equals 8, you can tell that f of 8 minus f of 0, okay, is equal to 43.6 repeating minus 1, which is 42.6 repeating. Yeah.
Can we just leave the C like C?
Mm-hmm. Yeah. When we're evaluating, this is called this is actually called a definite integral when it has actual limits. We're going to do indefinite integrals, which is when we're just finding the antiderivatives. So, and those are good questions. And when we actually start this unit, when I give you the assignment guide on Monday, then we start to do this formal, because I think this is a lot more fun doing it this way than following the book. Oh yeah, look at, they come in with their, that's it. I prefer Reese's, okay? Like the peanut butter cup ones, not the, well, vanilla, yeah. All right, you guys tell them what we did. All right, watch the Swivl. Okay, tomorrow we're going to take a look at the packet, and I'm going to show you an amazing thing that not only is this cool to tell you about a function, but it only opens the door for millions of applications. Millions.